Hey team, Andre from High Performance Academy here. Welcome along to this week's members webinar. Today we are going to be diving into cold start tuning using the Adaptronic modular series of ECUs. Obviously, we're going to be doing this on our FD RX7. In my opinion, this is one of those subtle little aspects that makes such a big difference to an engine that's been properly tuned and one that's been poorly tuned. What we're really looking for here is the sort of car where, regardless whether it's sub-zero and there's snow on the ground outside, or the engine is heavily heat soaked and it's been shut off for a few minutes, we basically want to be able to reach through the door, turn the key and have the engine start up and run perfectly. We're trying to replicate that factory quality tune. So we'll be diving into that as we get a little bit further into the webinar, but before we do that, just a few things that have been going on around here. And unless you've been hiding under a rock, you may have noticed it's been Black Friday and Cyber Monday. There's been sales all over the place, and High Performance Academy has been no different. I just want to bring your attention to the fact that our Cyber Monday sale is finishing in about a day. This is without a doubt the best sale we have ever run, and we are doing currently 50% off the value of every course we offer. We have never done anything like this before. I'm not sure if we're going to repeat it as well. So if you have been on the fence and maybe you've been thinking about jumping in and getting an HPA course or a few of our courses, this is the cheapest way to do it, but it is only running for about another 20 odd hours. So you will have to be quick. So we'll just quickly head across to my laptop screen and I'll just show you how it works. First of all, you'll see this convenient little countdown timer that's going to tell you exactly how long that deal is left to run. And if you do want to have a look at the courses that are available, click the Learn Here button. That's going to take you through to our courses page. Once that loads up, you'll be able to see all of the courses here, and if I wasn't logged in, you'll be able to see the price as well as the sale price. So obviously got a fairly extensive catalogue of courses covering diesel and gasoline engine tuning, as well as performance engine building and wiring. So if you do want to learn a new topic, then this is the best opportunity to jump in and do exactly that. So check that out. All you need to do is go to our website at hpacademy.com /nothing actually, and up the top there will be that yellow banner that I just showed you. Click on that yellow banner and that will take you through to the page that we are looking at here. Remember, only 18 odd hours to go, so you will have to be pretty quick, and once that's done, it's done. Maybe next year, I don't know. Anyway, moving on, last webinar, I did mention that we had a problem crop up with our Racecraft 86. It's been the year for problems with our race cars. However, we're working through them, and for those who haven't been following us regularly, the problem we had with the car last time we took it to the track was a recurring issue with the drive-by-wire throttle going into fault. We basically tracked that down to an issue with the wiring through the factory bulkhead connector. Before I do that, I just want to quickly show you what that actually looks like in our data. So we'll head across to i2 Pro. The data we've got here, what we're looking at is our throttle position. So that's what the drive-by-wire throttle body is doing versus the throttle pedal. Throttle pedal is in orange, throttle position in green. This is kind of what it's supposed to look like. See that the throttle position is tracking the driver pedal pretty well. We'll fast forward through a little bit. We can see it is a relatively low frequency signal, so there's a little bit of error in there, but you can see there's a couple of bits where it looks like the throttle position is dropping out a little bit. I'm along here and we can see we've got a bit of a spike here where it definitely didn't follow what we were wanting the throttle to do. And then if I zoom through this a little bit quicker, we can see at this point here, the throttle has gone into fault and the ECU's basically closed that, and it doesn't really matter what the driver does with the throttle, which is this blip here, the throttle is dead. So he sourced the problem there, or traced the problem there to actually a weird fault with the factory bulkhead connector. The tension on the pins, the factory contacts through that connector seem to be problematic. It's not a widespread problem, can't find anyone else reporting that problem, but here we are. This is a problem on our car anyway. You basically wiggle that connector and you'd see the signals from the throttle position as well as coolant temperature, manifold pressure and oil temperature, I think it might have been, were all going haywire, so not ideal. This is what that factory connector looks like if we're on my laptop screen here. This sits at the back of the engine on the driver's side, being right-hand drive, so right-hand side of the engine bay anyway. It connects the factory harness through to the chassis harness. So in our car, this is all 100% stock. And again, no one else reporting these problems, so I'm not 100% sure. So what's going on there? But we wanted a rock-solid solution here. We've had this problem once before with a cam control input, and we definitely don't want to repeat it. So what we ended up doing was going for a solution which was a little bit cheaper than the likes of moving to an Autosport connector. So this is what Brandon's ended up fitting in place of that factory bulkhead connector. So this is a pair of circular mil-spec connectors that we sourced from milspecwiring.com over in the US. So these are a much cheaper, much more cost-effective option compared to the likes of the Autosport connectors, which I think I've got a relatively conventional Autosport connector sitting here. If I can open that up, and I mean, these vary dramatically in price, but you can easily be spending a couple of $100 on a pair of these connectors, depending on the number of positions, etc., and the specifics of the connector beyond that. But it's actually not the connector price that's the only issue there. The other aspect is that you are going to need some relatively expensive crimp tooling as well as positioners to go with this to work with the Autosport connectors and the contacts that they use, and that can be pretty off-putting. So those mil-spec connectors that I just showed you, which we'll show you where you can get them from in a minute, the nice aspect of these is that they are compatible with these generic crimp tools which I use for the DTM connectors, which we use a lot of. Anyone who's done just about any motorsport wiring or anything even on club level and street level cars, the DTM connectors, in my opinion, probably one of the most cost-effective solutions. This crimp tool here, about $50. Actually need two different crimp tools for our application because we've got both 16 gauge and 20 gauge contacts, but pretty cost effective, and I think the total sum parts that we put into that was about maybe $300 including the freight. So we'll just jump across to my laptop screen again for a moment, and this isn't a sales pitch. We purchased these from Milspec Wiring, and they're certainly not the only place you can get them from, but I just wanted to show you the sort of prices that you're looking at. So you know, you can see this particular one here, you're looking at $63. So these are also still compatible with a separate back shell that you can buy for them. So if you Tefsa wire and you want to add a heat molded boot to the back of it, which we would do with an Autosport connector, totally achievable there as well. So just a slightly cheaper alternative to the Autosport connector, something that we do get often asked about with our wiring webinars. Are there cheaper alternatives to Autosport connectors? Well, yes, there are. Are they as good? No, probably not quite as good, but particularly for a street or a club level car, probably superior, let's hope, to the factory connector, and we'll see how that works out in terms of reliability as we move on. Now, another thing we have been changing on the car, we can't jump over to my laptop screen. It is a bit of a mess in here. It's a little bit hard to see, but over here in the opposite corner of the engine bay, we have an IAG Air oil separator. Now, for as long as I can remember, we've had a pretty conventional oil catch can fitted in this location, which does work to a degree. The problem with a conventional catch can is what we're doing is running the breathers up into that catch can, which ends up trapping a lot of oil vapor or oil droplets with the vapor, the blow-by gases that naturally we are going to see in any engine. The boxer engine, the horizontally opposed engine in the Subaru, does seem to be a little bit more susceptible to actually pushing oil through those breathers than a conventional inline style engine or V configuration engine. So the options that you've got here, originally what I actually had on the bottom of that catch can was a drain which we could take back to the sump. So basically the idea would be that the catch can would catch oil and air, separate the oil out to a degree which is going to sink to the bottom of it. It had a breather, exactly the same breather that we can actually see on that IAG catch can, so the blow-by gases would be vented into the engine bay. So a couple of problems with that. First of all, difficult to do a really thorough job of separating the air and oil with a conventional catch can, or at least the design we had. So inevitably you get the risk of ending up with oil vapor blowing out of that filter as well, which kind of makes a mess in the engine bay. And one thing I hate in an engine bay is oil mess everywhere. Try and stay away from that wherever possible. So that's the first problem. The second problem is that while yes, you can release the oil that you catch back into the sump, you do end up with a lot of other nasties, condensation and stuff getting into that catch can as well. And yeah, I don't know if anyone's actually looked at what collects in the bottom of a catch can, but it's often not that pretty, and I'm not too sure if I would personally like to return that to the sump. So the air oil separator works on a slightly different principle, and what it does, as its name implies, it separates the air, the blow-by gases, from the oil vapor. Then the oil is going to be collected in the bottom. So far, not too big of a difference, but it does a much better job of separating the air and oil. So then what we've got coming out of that vent is, or should be, pretty much pure blow-by gases, no oil contained. Then the other part that's nice is it does return the oil back into the crankcase through the crankcase breather. All right, all well and good, I hear you saying, but we've still got this problem of condensation and nasties going back into the sump. Well, that's where this is different. What it does is it actually includes a bypass for coolant to be flowed through this. And what this does, while it is a bit of a pain to plumb up, requiring you to intercept a couple of coolant lines on the vehicle, when that's done, the coolant passing through this basically has the effect of getting rid of the condensation and boiling off any nasties in there. So we are hopefully returning pure oil back into the sump. So now, while the IAG system doesn't actually have a lot of information about that, if we head over to my laptop screen, Radium, there's a bunch of manufacturers making these. Basically, they all work on the same principle. They had a little bit more information on the Radium website about how this works. So, for example, this little unit here, this is what's in the bottom of it, which is the heater unit. So this is where the coolant goes through in the Radium unit, and basically that's going to, again, get rid of all of the condensation out of there. And you can sort of see, if I zoom in on this a little bit, a bit of an idea. So there's basically a matrix here that allows the oil and air to be separated. This one actually also includes a dipstick. We've got a condensation trap, which is this bottom section here. So that traps all that condensation, making sure that only the oil is returning. And then it's got the coolant port here with that heater, which I've just mentioned, which is meant to get rid of that condensation. So far, we tested that very briefly at the track, and it seems to have been a massive improvement. The problem with the system we were running is because it does end up pushing a reasonable amount of oil into that catch can, you need to be quite mindful of topping up your oil level, which we don't really want to be doing during a race meeting. This way it is 100% maintenance free, which I'm a big fan of. So that's only just gone in. It's definitely not a new technology, but I just thought I'd talk about it there. Another thing that is a reasonably new technology is this little lambda sensor that I've got in front of me. Now, probably on face value doesn't look too new. This is a Bosch LSU ADV sensor, so a little bit different to the conventional LSU 4.9 lambda sensors that everyone's running. So these are designed by Bosch with the intention of being able to be mounted pre-turbocharger. So the advantage with this is the sensor is designed to be a little bit more heat resistant, so this can operate continuously at up to 980 degrees C, whereas the conventional LSU 4.9 operates at 930 degrees C continuous, with momentary operation up to 1030 degrees C. So this is going to be suitable for a fairly wide range of applications, particularly for those looking at extreme heat applications with their exhaust gas temperature. These are not directly compatible with an LSU 4.9 controller, though there are some significant differences. First of all, there is no calibration resistor with the LSU ADV sensor, so very different to the earlier sensors that have all included a calibration resistor. This means it is going to require a specific controller. This is limited right now. The reason we've got this is because the Emtron KV8, which we've just filmed a worked example on with a Nissan R34 GTR. Emtron is probably one of the first aftermarket ECUs that I'm aware of, probably I'm guessing outside of Bosch, that will support the ADV sensor. Now we'll see this become a little bit more prominent, I think, as that sensor becomes more commonplace, but watch out for that because it is something that will become more prominent over the next 6 to 12 months, I would imagine. Our YouTube release for this week, last week I think, anyway, I'm going to talk about it because I think it is one that a lot of people should be watching. And I'm just going to turn the volume back down so that I don't end up trying to talk over myself. So this is step 10 actually that we shot of the adaptronic modular tuning process, the HPA 10-step process being filmed on the adaptronic modular, which is the process of completing the tune at the racetrack or on the road if you don't have access to a racetrack. We're pretty fortunate in that regard there with our access to Highlands Motorsport Park. But the idea here is that even on a really well-developed professional dyno, it's very hard to perfectly replicate the temperatures, pressures, airflows, etc. that we will see at speed on a racetrack or out on the road. So we can often find subtle differences, particularly with our air-fuel ratios and our boost pressure out on the road compared to what we saw on the dyno. With turbocharged engines as well, particularly we're likely to see differences in our boost control strategies required. This is very, very common on transients or where we're in and out of the throttle on a gear shift. We might get really good control on the dyno and might start to see overboosts or differences between our desired boost pressure and our measured boost pressure on the track. So it's really important. It's an area that I don't see a lot of professional tuners doing. Most tuners run the car up on the dyno, finish the tune on the dyno and send it out the door. For as long as I've been tuning, I've always confirmed my tunes out on the road wherever possible, and I believe it's really essential to get the results absolutely perfect and be confident that they are going to be right when the car's given back to the owner. So if you want to check out a little bit more about what's involved in the road tuning process, check out that video on our YouTube channel. If you've got questions on that video, ask. If you aren't already a subscriber, make sure you do subscribe and also turn notifications on, and this way you won't miss out on any of our future videos. Also this week, recently, we released another video which you may be interested in watching as well. You'll find that of course on our YouTube channel, but it's all covering this little guy here, which is a drive-by-wire throttle motor that is being used for a blow-off valve. And this isn't very common. It's not completely new technology. Yes, it's been around. We've actually covered it before on a couple of drag applications, but this was actually one of the vehicles that was racing at World Time Attack back in 2019, I think. They didn't run Time Attack last year, this year unfortunately, due to COVID and a range of other things, but this is on the Global Aircraft Services Mitsubishi Evo 9 Time Attack car. And one of the problems we see with the larger turbos that are being now used on small capacity engines is that yes, we need that bigger turbocharger if we want to make insane power levels, which these cars are producing. However, we can find that we are starting to operate dangerously close to the surge limit with these turbochargers, particularly if we operate the engine down at lower RPM where its volumetric efficiency isn't so good. And the drive-by-wire throttle can be used here. It's only a small one. It can be used as a conventional blow-off valve, so really no difference there compared to a conventional blow-off valve or recirculation valve. But the other key aspect is that it can be used here to relieve surge. So this requires some special control strategies and programming. But essentially, if the engine drops down into an RPM range where surge is likely and the boost pressure is still high, which we can see with a sequential gearbox or a paddle shifted gearbox, if the driver short shifts a gear and it drops the engine down in the RPM, because the shift is so quick, the boost pressure doesn't tend to drop away, and that's where we risk running into surge. So the drive-by-wire throttle body can be programmed to open a preset amount to just relieve a little bit of that airflow and move the turbocharger away from surge. So if you are interested, again, video covering that on our YouTube channel. All right, that covers just about everything that we were going to talk about today, but just one last time before we move into our webinar. Cyber Monday sale, only about 18 hours left. Head over to hpacademy.com if you want to grab a great deal on any of our existing courses. Thanks for watching there. Give me a few moments and we'll get started with today's lesson. If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.